You may think it's just a lot of empty space out there. But there's more in outer space than meets the eye. Our solar system is swarming with asteroids, scrap pieces from its genesis 4.5 billion years ago. Again and again, these pieces collide. And even our home planet is a target. Above the Russian region of Chelyabinsk, a meteoroid explodes, spreading destruction and injury.
Here is an event happening that shows us that this is not just a theoretical subject, one that happens every few million years in Earth history. It happens now. It happens all the time.
To life on Earth, cosmic debris poses a real threat.
If we really think we want to stay around on this planet for a long time, hundreds, thousands of years into the future, this is something we have to deal with.
The meteorite that hit what is now Mexico 65 million years ago is a memento. It became famous as the Dino Killer.
The dinosaurs did not have telescopes, and they did not have a space program, and they are gone. We don't want the same thing to happen to us.
So let's be alert. Celestial missiles aimed at us. That's what astronomers are watching for. On the very day of the Russian meteor strike, an asteroid barely missed planet Earth, a very recent double event, and an ominous reminder of the meteor menace. Arizona Badlands. This desert boasts a striking geological formation. Meanwhile, a prime tourist destination. Even a layman will guess that here, some violent cataclysm has inscribed itself in the geological record. But he is not a layman. Christian Coburl from Vienna University is an impact expert, and this feature is among his specialties. Its name says it all. Meteor crater. Christian tries to visualize the scale of an event that would leave behind such a crater.
About 50,000 years ago, an asteroid was hurtling towards Earth with a speed of maybe 15, 20 kilometers per second. And it was crashing through the atmosphere. And the asteroid was burying into the ground a little bit and then exploding. The energy that was released was so large that within a few seconds, a crater about 20 times the diameter of the asteroid itself was excavated. Not only the energies involved, which are about 1,000 times that of a Hiroshima atomic bomb, but also the speed with which all this happens. So this is something that we don't see anywhere else in the geological record. There are no other geological processes that can do things like this.
Meteor crater is the best preserved meteorite impact site on Earth. Upon impact, the meteorite vaporized almost completely. Huge chunks of bedrock lie scattered around the crater rim. Other bits were hurled several miles into the surrounding landscape. Moonrise in the night sky. Earth's natural satellite is itself the result of a cosmic crash. The assumption is that a small body called Theia collided with young planet Earth some 4.5 billion years ago. The debris hurled into space was eventually compacted into a new object, a natural satellite circling the young Earth. Some 4.1 billion years ago, this new moon suffered a phase of massive bombardment. This bombardment has pockmarked the face of the moon forever. Over billions of years, meteorite showers have continued to scar the lunar surface. NASA's Lunar Reconnaissance Orbiter is taking a close look at the moon. Its craters are carved in stone. Without atmosphere or liquid water, there is no erosion, so the scars remain unchanged until new collisions create more craters. The young Earth was also hit by countless meteorites. They brought precious gifts from the universe: gold, platinum, and iridium. Cosmic missiles have continued to leave ever-new traces on our planet. And yet, very few impact craters are known, a mere 180. Why is that? On the one hand, almost 3/4 of the Earth's surface is ocean. On the other, impact traces on land have been eroded and erased by water, wind, and ice. But cosmic missiles are still peppering the Earth, and we can even see them, shooting stars and fireballs in the night sky. February 15th, 2013. Out of the ethereal blue over Russia's Chelyabinsk region, a giant fireball suddenly appears. A cosmic body has approached, undetected. The location of the impact is in Russia, east of the Ural Mountains, near the Kazakhstan border. It's an asteroid, about 66 feet in diameter, and it explodes in the Earth's atmosphere, near the city of Chelyabinsk. The local population is in a panic. The massive shockwave of the exploding meteoroid shatters windows and glass fronts of thousands of buildings. Even a factory roof collapses. The total damage is enormous. This incident left some 1,500 people injured, mostly from flying glass. It's an historic event. Never before in recorded history has a civilization been hit so dramatically by a cosmic body. Fortunately, this cosmic bomb never hit the ground, but exploded up in the atmosphere, some 15 miles high.
Here is an event happening that shows us that this is not just a theoretical subject, one that happens every few million years in Earth history. It happens now. It happens all the time. And it is something that we can learn a lot from. There's already calculations of the orbit where this asteroid was coming from. It tells us something about how these asteroids react with the Earth atmosphere. Never before have we had so much data about an explosion in the atmosphere like this, and we always have to remember this is a small event.
This gravel pit of the solar system is the scene of frequent collisions which send asteroids on trajectories close to Earth. Some of these near-Earth objects, or NEOs, are potential threats to our planet. NASA's Jet Propulsion Laboratory in Pasadena, California, the main center for detecting and tracking near-Earth objects. Don Yeomans is head of the NEO program.
Well, it's near-Earth object potential impacts is a relatively new field, because until the 1990s, astronomers really weren't looking for these objects, and it was only about 1998 when NASA-supported facilities started looking every night for these objects that we discovered so many. So it's comforting to me now that we are looking and we are finding these objects, and once we find them, we can track them with additional observations, we can compute their orbits, trace their trajectories for 100 years into the future, and see if there's any interesting close Earth approaches or are there any possible impacts.
These radar images show the asteroid 2012 EA-14. By coincidence, on the same day a meteorite air-blasted over Russia, this 130-foot object was also heading towards the Earth. The asteroid passed above Indonesia at a distance of only about 18,000 miles, within the orbits of geostationary satellites.
Such small objects that are in the 10, 20, 30, 50, 100 meter range, they can come anytime out of the blue sky. And I think this is one of the main messages that the events on the 15th of February 2013 tell us. There's a lot out there. Let's watch out.
Mount Haleakala on the Hawaiian island of Maui. 10,000 feet above sea level, astronomers are searching for near-Earth objects. The centerpiece of the International Pan-STARRS project is a unique telescope. PS1 is a giant wide-angle lens. It surveys a much larger section of the sky than normal telescopes. Pan-STARRS is also equipped with the world's biggest digital camera. Each image has 1,400 megapixels, roughly 100 times the resolution of an average SLR camera. The telescope is operated from the control center at the foot of Mount Haleakala, an hour's drive from the summit. Each night, surveys are coordinated from here. The telescope captures huge sections of the sky with extreme accuracy. In addition, the system scans for moving or changing objects.
140, 150.
In this search for near-Earth objects, sections of the sky are defined and systematically surveyed. The telescope scans each field twice, at 15-minute intervals. The result is a massive amount of data to be processed by astronomers at the University of Hawaii in Honolulu.
Pan-STARRS, any other discoveries at the time of discovery? So
Officially, the telescope on Mount Haleakala has been in operation since May 2010. Meanwhile, some 300 near-Earth objects have been detected. Larry Deno uses a special program to visualize newly discovered NEOs. The red paths show those near-Earth asteroids and comets discovered by Pan-STARRS. Several of them seem to almost touch the Earth. But this image only shows one level. Many objects speed past far above or below it without endangering Earth. The scientists have ways to spot suspicious objects in their images.
we do a mathematical operation we call image subtraction from using those two images. And what you're left over with when you do an image subtraction is something that's moving will have positive pixels in the first image, negative pixels in the second image. So on the screen we have the first image, which is what the sky would look like if Pan-STARRS took a picture of it. 15 minutes later, we have the same part of sky, and there's an asteroid in the data that's hard to see, but it's moved a little bit in those 15 minutes. And when we subtract the second image from the first, most of the stars disappear, and what you have in the middle is this asteroid that's moved a little bit over the 15 minutes.
According to a new NASA study, there are approximately 5,000 potentially hazardous asteroids wider than 300 feet. So far, the search programs have only been able to identify 1 out of 4.
What we need is our telescopes like Pan-STARRS that have very wide fields of view, that can be read out very quickly, that have a lot of data processing capabilities that you can analyze the images very quickly and detect the asteroids efficiently. So we know how to do that, but having bigger telescopes, having more telescopes, and also having some small telescopes that have extremely wide fields of view that can image the entire sky every single night could be really important.
A second Pan-STARRS telescope is already in development. Asteroids have left scars on the face of the Earth. Satellite images show these features around the globe. But it's often unclear whether these are really impact craters. By the end of 2012, 183 meteorite craters were known. Number 182 is confirmed only recently. In a remote area in the east of the Democratic Republic of Congo. The Louise Formation was first described in 1919, but it's never been studied. French scientist Ludovic Ferrier curates the rock collection at Vienna's Museum of Natural History. He wanted to find out whether the crater really results from an impact. Virtual images were not enough. Ludovic needed to see the real crater. So he launched an expedition to the remote site in the Congo.
Then in the field, it was very difficult to reach the structure itself. And after several days looking around in the grass and along rivers, we finally end up with my assistant in an outcrop. And we found out these rocks. And I was really, really excited when I saw it. It was the first occurrence of a shatter cones in these structures. Already in the field, finding such type of fractured, I was able to say for sure, almost for sure, that it was the site of a very big impact.
Fan-shaped shatter cones like these are evidence of shock waves in the bedrock, and there are even more hints. Thin sections were cut from the samples of the Louisi rock. Under a light microscope, the composition of the rock is revealed. Ludovic Ferrier looked for very specific patterns in the mineral components. For impact researchers, there is one reliable proof of a meteorite impact, a characteristic telltale structure in grains of light-colored quartz. Ferrier found what he was looking for, grains of shocked quartz. These crystals are crisscrossed by distinctive lines. The lamellae are caused by shock waves of a meteorite impact. Finally, Ludovic Ferrier found confirmation that the Louisi Formation really was a meteorite impact crater, the first such discovery in Central Africa. Scientists estimate that every day, approximately 100 tons of material from space hits the Earth. April 22nd, 2012. A rock enters the Earth's atmosphere. By coincidence, a camera records the fireball. At this point, the rock is at least the size of a washing machine. But in the end, it breaks up, and a meteorite shower hits the ground. Coloma in California, a historic place. This is a replica of Sutter's Mill. During the construction of the original sawmill in 1848, a worker, James Marshall, discovered gold and triggered the famous California gold rush. 164 years later, the Sutter's Mill meteorite triggered a scientific gold rush. Peter Jeniskins works for NASA and SETI, the search for extraterrestrial intelligence. Supported by a team of volunteers, here, Peter is searching for meteorites. The terrain is confusing, the weather hot, but the mood is optimistic. The team is looking for small pieces of meteorite in the thick grass. This is a real challenge, even for the expert. Geologist Peter Jeniskins is looking for meteorites, but he needs to keep a sharp eye. Apart from true meteorites, there are plenty of false ones, called meteorongs.
This is one of the 4 or 5 different meteorons. Serpentines like this, basalts, charcoal, asphalt, and poops. Various forms of poop are very much looking like you're searching for.
The saying goes that he that seeketh findeth, but success has been slow coming. Others, like Park Ranger Suzanne Madden, did not seek all that hard. She simply had luck on her side.
I literally was just walking in the park, and I happened to glance down, and I had just seen one of the meteorites that the NASA crew, the SETI crew, had found. And so I looked down and I thought, gosh, that looks like what they just showed me. And then I showed it to Peter, and he said, yes, it was a meteorite. So it was really funny because I was so not looking. And it seems like that's been a majority of the ones that have been found have been people that weren't actually looking for them. And the amazing thing is I found it probably 150 yards from the original gold discovery site.
Another chance find must be verified by Peter Jeniskins.
This is a real meteorite. Congratulations. Wow, look at that. So this meteorite is really special because it broke very late during the coming down into the Earth's atmosphere, because you can see it was split in two. and then the split side was fully crusted, so it was crusted over. So that meant that very deep into the atmosphere this thing broke, but it was still going so fast that the surface melted. This meteorite is also special because it was moving through the atmosphere. It did not tumble around. It really went like this. And we can say that because it was bleeding over the melt layer to the backside of this meteorite.
By the end of 2012, around 75 pieces of the Sutter's Mill meteorite were documented. The biggest weighs half a pound. This one here, just 8 grams. NASA's Ames Research Center in Mountain View, California. One major focus of research is the origins of life on Earth, and possibly in space. Scientists at the Astrochemistry Lab investigate how and where in space organic substances are formed. To carry out their experiments, they mix various chemical compounds. In the end, these cocktails are supposed to produce complex organic molecules. Ultraviolet radiation, a vacuum, and temperatures close to absolute zero. Here, researchers simulate extraterrestrial conditions. They produce ice of the type occurring on comets or planets. Scott Sanford is in charge of these experiments. One goal is to find out how chemical precursors to life form in the universe and what they are.
The organic inventory of meteorites is actually quite diverse. People have found amino acids in them, and these are the building blocks of proteins, which we use for all kinds of things in living systems today. The nucleobases are found in meteorites, and these are the compounds that are the building blocks of RNA and DNA. So a lot of the basic kinds of molecules that play a real key role in life on Earth are found in meteorites, and in many cases we can make those non-biologically using processes that happen in environments that are not unrealistic for what we see out in space.
Does this mean that organic life is common in the cosmos? What are the odds that extraterrestrial life exists?
All I can tell you is that everything I've done over the last 30 years and my experience tells me that these building blocks are just out there all over the place. The universe is an organic chemist. It's not a very efficient one, but it has very big beakers and a lot of time. So a lot of organics out there.
And thus, it seems merely a matter of statistics whether life could emerge on other planets in space, thanks to a little startup help from meteorites. To better understand what happens in nature when a meteorite hits the Earth, scientists produce meteorite strikes in the lab. This is done at a special facility in southwest Germany. Preparations are underway for a spectacular experiment. A 1-ton block of sandstone is about to become a target. The steel projectile in the cylinder will play the role of the meteorite. The experiment will be carried out with a 2-stage light gas gun. The plastic piston is accelerated by detonating 3 pounds of explosives. The piston compresses hydrogen gas in the gun to around 36,000 psi. This overload pressure propels the steel projectile towards the target. The sandstone block is wired up to record the effects of the impact. The colors of the target are to make it easier to attribute the debris. Since the procedure is extremely fast, it is filmed with a high-speed camera. The moment has arrived. The bunker is closed. These massive walls are needed because extreme energies are unleashed. A few final settings are made in the control room. Then, the accelerator is activated. The countdown starts.
3, 2, 1, Feuer.
The engineers and scientists are eager to see the outcome. First of all, the researchers collect all the fragments. Their size and dispersion provide important information about the impact. Frank Schaefer from the Ernst Mach Institute in Freiburg, Germany, examines the crater. The procedure only lasted between 20 and 30 milliseconds and was filmed at 54,000 frames per second. After a flash of light upon impact, the displaced material is hurled out. The scientists are satisfied. The steel projectile had a speed of 2.7 miles per second, more than 10,000 miles per hour. These experiments are part of the MEMEN project. The researchers want to reconstruct actual meteorite impacts, for until now, no impact has been studied live. Ambitious goals at any standard. At the Berlin Natural History Museum, Kai Wunemann is also working on the MEMEN project. But he looks at meteorite impacts from a different perspective. Kai Wunemann simulates meteorite impacts in a computer as realistically as possible. Kai and his team compute numerical simulations of cosmic strikes. In the MEMEN project, Kai uses data from the ballistic tests in the laboratory. The computer model for this kind of virtual experiment is complex enough. For example, simulating the damage to the sandstone block. But a physical meteorite hit is a different matter.
You can't resolve a single grain in a rock, and at the same time, rock units of hundreds of meters. In reality, you basically run two different models and resolve a single process, try to understand what's happening on a very tiny scale, try to make some generalizations from what you see there, and then put these information into a large-scale model.
However, the art of the scientists is to extrapolate lab results in order to understand real-life occurrences. Such simulations are meant to help predict the effects of an asteroid impact. Because one thing is clear, the next hit is merely a matter of time. There are plenty of ideas about how to protect the Earth from potential impacts. One example is a spacecraft with a laser system. The laser beam would vaporize material on the surface of the asteroid. The recoil would gradually push the asteroid from its collision course. Another idea is the gravity tractor, a massive spacecraft that would be positioned near the asteroid. Relying on the gravitational attraction between the two, the spacecraft would be able to pull the object off course. There is another idea, the tough approach, intercepting asteroids on collision course. Some scientists are itching to literally knock out such dangerous missiles from space. Alan Harris is an enthusiastic snooker player and one of the world's leading asteroid researchers. With his team, Alan is working to save the Earth, if worse should come to worst. Alan works at the German Aerospace Center in Berlin. He is in charge of the NeoShield project. Launched in early 2012, it is the first international project for deflecting asteroids.
So in a sense, we're playing cosmic billiards in that we are striking the asteroid with our spacecraft, and we're looking at a transfer of momentum, right? There are two things that come into this, conservation of momentum and conservation of energy. If you've ever played snooker or billiards, you'll know all about those things.
For a planned defense action, scientists first analyze key properties of an asteroid: size and shape, composition, and rotation. One source of information about asteroids is their light curve. A simple experiment illustrates the importance of the light curve. The spotlight represents the sun. A model asteroid serves as a test object. When the asteroid rotates, its brightness constantly changes. The interplay of light and shadow reveals the body's form and rotation rate. Rotation is important if an asteroid is to be knocked off its path.
What we're interested in with NeoShield is the next one, right? The next object that we are going to be so worried about that we think we should do something about it. We should launch a mitigation mission. Now, that will come one day, but it won't be a big object. It'll be something of the order of between 50 meters and 200 meters in size, okay? And that's relatively easy to deal with. The impact of an object like that could be very serious. It could largely destroy a city like Berlin, Paris, London.
One of the partners in the NeoShield project is the Fraunhofer Institute for High-Speed Dynamics in Freiburg, Germany. Ballistic tests are also carried out here, albeit on a smaller scale. The space gun is loaded for the next experiment. In this NeoShield experiment, a 10-pound sandstone cube will be shot at. The unusual thing is that the block is suspended to swing freely, representing a flying asteroid. Here, too, health and safety is a priority. The space gun shoots projectiles at speeds of up to 22,000 miles per hour. The block of sandstone is ready. A few final adjustments are made, and the gun is ready to fire. Impact and ejection happen so quickly that the massive block has had no time to swing. The scientists, led by Frank Schaefer, study the video to see how big the pieces of debris are after impact and how much the laboratory asteroid was moved in the end.
In the experiments, we observed that large quantities of rock are hurled from the crater in the opposite direction of the projectile. This recoil gives the rock that we shot at additional momentum, so that it is knocked off its position even further than only by the actual momentum of the impacting projectile.
The results of these ballistic tests will be used in the NeoShield project, as will the data and findings of the other international research institutes and companies participating in the project. Based on technologies available today, the scientists have drawn up a scenario for deflecting an asteroid on collision course. First, an observer spacecraft would be used to fly toward the asteroid to measure and study it as accurately as possible. The data would enable scientists to precisely adjust their impacting tool. Then, the kinetic impactor is launched. A flying battering ram. The biggest challenge is hitting the asteroid in exactly the right place to achieve the greatest effect. Ideally, the impactor spacecraft would hit the asteroid with sufficient force to deflect it. To demonstrate that their plan would work, the NeoShield scientists would eventually like to launch a mission to push a real asteroid off course. At any rate, it is clear that in the long term, humankind has to brace for a potentially disastrous impact.
For me, it's a technical challenge, a scientific challenge. I'm not worried about it. I wouldn't expect anybody else to be worried about it. But for the long-term survival, if you like, of mankind, or the long-term development of our civilization on this planet, this is really something we've got to worry about.
We don't want to be caught by an incoming asteroid that we didn't see coming. So let's build a survey telescope in space. Let's build one on the ground. Let's make sure we find the next asteroid before it finds us.
Near-Earth objects always get what I call bad press because they're threatening objects. People worry about them, but subsequent collisions of these objects with the Earth punctuated evolution, allowing the most adaptable species, mammals to progress further. So in some sense, we owe our very existence and our position atop the food chain to these near-Earth objects.
Because they happen in geological time periods, so with very long intervals in between. I don't think we need to be afraid right now, but in the future, impacts will happen.
This time, it wasn't the end of the world. But there's no doubt that another asteroid will come towards us, headed for collision. The only question is, when?